All right, this is Baby Real Analysis, and this is video 4 to the integration series. And in the previous video, we gave brief introduction into Darboux integration and focused more on the prerequisite information dealing with refinements and partitions. So in this video, we will actually go more into Darboux integration, but first we'll still kind of touch on some prerequisite information or theorems before doing a proof of a Darboux integration theorem at the very end of the video. So previously we stated if Q is a refinement of P, so it has the same partition points as P, but also has finitely many more points, then the lower sum with P is less than or equal to the lower sum with Q, which is less than or equal to the upper sum with Q, which is less than or equal to the upper sum with P. All right, so this theorem that I have the proof written out, so the theorem is L of F is less than or equal to U of F. So recall that L of F is the supremum of the lower sums for all partitions. And in this case, I'm calling it Q so that it can be any partition. And U of F is the infimum of the upper sums of all partitions P. So to prove this theorem, we're going to use J. Cummings exercise 8.3, which states that if you have two subsets of real numbers, A and B, that are non-empty, and we have that for all X and A and Y and B, if X is less than or equal to Y for all X and A and Y and B, then the supremum of A is less than or equal to the infimum of B. So that's going to actually be applied in this proof. All right, so now the actual proof. So we're going to choose two partitions P and Q, where P is the partition consisting of X naught, which is, so we have our endpoints A and B, where X naught is A and Xn is B. Q is going to be another partition, except now I'm using the letter Y for the different values of that we're using as in the partition Q. And so we're going to form a partition D, which is equal to A, our endpoint, which is equal to Z naught less than Z1 dot 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 less than ZL, which is equal to B. So we're going to form this partition D, and each of the ZI's is one of the XJ or YK from P and Q, and all of the XJs and YKs are present in D. So we've essentially made a refinement D, and it's a refinement of both P and Q. Hence, we have that the lower sum of P is less than or equal to the lower sum of D, which is less than or equal to the upper sum of D, which is less than or equal to the upper sum with P. And the same thing for Q. Lower sum of Q is less than or equal to the lower sum of D, less than or equal to the upper sum of D, and that's less than or equal to the upper sum with Q. So for any partitions P and Q, we can form a refinement D such that the lower sum with P is always going to be less than or equal to the upper sum with Q, because of it being this refinement D from both of those partitions P and Q. So in other words, the lower sum with P is less than or equal to the lower sum with D, which is less than or equal to the upper sum with D, and that's less than or equal to the upper sum with Q for any partitions P and Q. So for all partitions P and Q, the lower sum of P is always less than or equal to the upper sum with Q. And using exercise 8.3, since that's the case, since all elements of the lower sums are less than or equal to all elements from the upper sums, then the supremum of the lower sums, in this case with partition of all partitions P, is less than or equal to the infimum of the upper sums of all partitions Q. Well, that's the same thing as just saying L of F is less than or equal to U of F. All right, so that's the proof for that theorem. And here's a lemma that I thought was interesting. It's from Jay Cummings' long-form real analysis textbook. And you have a function that's bounded. Let's say little m is less than or equal to f of x, which is less than or equal to capital M for all x in a, b. Then we have that little m times b minus a is less than or equal to L of f, which is less than or equal to u of f, which is less than or equal to capital M times b minus a. And so just to visualize, so we have this function that's from a to b is in blue, and we have the lower bound and upper bound, where little m is a lower bound and capital M is an upper bound. And if we use a partition where it's called a 2-point partition, I'm calling it P star, that's consisting of just the endpoints, then since little m is less than or equal to f of x, which is less than or equal to capital M for all x in a, b, then the lower sum with this 2-point partition, which is equal to the summation of the infimum of the function for each subinterval xi minus 1 to xi times the lengths of that subinterval xi minus 1. But we only have one subinterval, it's ab. So the lower sum with this 2-point partition is equal to the infimum of the function on x naught to x1, where x naught is a and x1 is b. All right, so that's why it's equal to the infimum of the function on the entire closed interval AB times B minus A. That is the lower sum of our 2-point partition. But since the little m is a lower bound, it's going to always be less than or equal to the infimum of the function on that closed interval AB, which would imply that this little m times B minus A is less than or equal to the inf of the function on AB times B minus A. And that's the same as just saying little m times B minus A is less than or equal to the lower sum of this 2-point partition P star. And similarly, we get a similar thing with the upper sum of this 2-point partition, except that the upper sum, the sup of the function, that's the greatest lower bound of the function, is less than or equal to any upper bound. The least upper bound of the function is less than or equal to any other upper bound. So you could say sup of fx on AB is less than or equal to capital M, which would imply that the upper sum of the function, which is the sup of the function on the interval AB times B minus A, that's for our 2-point partition, that's less than or equal to capital M times B minus A. All right, so it's going to rely on us making this 2-point partition and getting a string of inequalities to get down to this being little m times b minus a less than or equal to L of f, which is less than or equal to u of f, which is less than or equal to capital M times b minus a. And so you could see that the green rectangle is that's our lower sum with partition P star, where that's our 2-point partition. And the purple rectangle, which would include the green one as well, this whole purple rectangle is the upper sum with our partition P star. Okay, so now the actual proof. So let f be bounded. Suppose little m is less than or equal to f of x, which is less than or equal to capital M for little m and capital M, the real numbers, and this is true for all x in AB. So the most simple partition is the 2-point partition, consisting of the endpoints A and B. And this 2-point partition, I'm calling it P star. So P star is equal to A, which is our x naught, less than x1, which is equal to b. So we know little m is a lower bound to the function, so little m is less than or equal to the infimum of the function on the entire interval ab. That's if and only if little m times b minus a is less than or equal to the nth of the function on ab times b minus a. Well, that's the same as little m times b minus a less than or equal to the lower sum of our partition, 2-point partition p star. And I labeled it with a green star because we're going to use this. Similarly, the capital M is an upper bound, so it's going to be greater than or equal to the supremum of the function on the entire interval AB. And since that's the case, then capital M times B minus A is greater than or equal to the upper sum with our 2-point partition P star. And I'm labeling that part double star. All other partitions P and Q are refinements of the 2-point partition P star, because all other partitions P and Q are going to contain those two endpoints A and B. So let L of F be the supremum of all lower sums of partitions P. Let U of F be the infimum of all upper sums of partition Q. We know by previous theorem that L of F is less than or equal to U of F. So combining this with star and double star, we can say that for all partitions P and Q, and the fact that they are refinements of our 2-point partition P star, we have the following string of inequalities. So it's a pretty long string. So we have little m times b minus a is less than or equal to the lower sum with our 2-point partition P star, and that's based off of star. And our lower sum of partition P star is less than or equal to the lower sum of all partitions P, because of it, P's a refinement of P star. And we know L of F is the sup of all the lower sums. So the lower sum of all partitions P is less than or equal to L of F, since L of F is the sup of lower sums. All right, and then we know that's less than or equal to U of F by previous theorem. And then U of F is the infimum of all upper sums. So U of F is less than or equal to the upper sums of all partitions Q, because U of F is the infimum of all upper sums. But then we know all partitions Q are a refinement of partition P star. So the upper sums with Q is less than or equal to the upper sums of P star. That's our 2-point partition. So that's because of the refinement. But then we know that the upper sum of P star is less than or equal to capital M times B minus A. And that was from double star. So we get that M times B minus A is less than or equal to L of F, which is less than or equal to U of F, which is less than or equal to capital M times B minus A. All right, so that completes the proof of that lemma. Now we're finally into the actual Darboux integration. So a function is Darboux integrable when it's, so the L of F equals U of F. So when the supremum of the lower sums is equal to the nth of the upper sums. And we define the definite integral AB to be just equal to this L of F, which is equal to U of F. So the theorem that we're going to prove states that if we have a bounded function, this bounded function f is Darboux integrable if and only if for all epsilon there exists a partition calling it P of epsilon, so that the upper sum of this partition minus the lower sum of this partition is less than epsilon. And we see that there's no absolute value that's necessary, because then the upper sums are always greater than the lower sums. All right, so the proof. So we're going to have some function, bounded function f. In the forward direction, we're going to assume f is Darboux integrable. All right, so first forward direction. Let's let f be Darboux integrable. Well, if that's the case, then we know L of f is equal to U of f. So then we know for all partitions Q and all partitions P, we have that the lower sums of all of this, so the lower sums, let's say with P, is less than or equal to all of the upper sums of partitions P. And we also know, what else do we know? That the lower sums P is less than or equal to the L of f, because L of f is the supremum, so L of f is the sup of all the lower sums, and in this case I'm using all of partition P, and then U of f is the inf of the upper sums with partition Q. So let me erase this, change that to a Q. Okay, so that's L of lower sums of P are less than or equal to L of f, and we're assuming that's equal to U of f, since we're assuming Darboux integrable, and U of f is going to be less than or equal to all partitions Q. And just stating what we know. Now, what are we trying to show? So let me put in a different color. This would be like not part of the proof, but it is helpful to know what are we trying to show. So we're trying to show that for given epsilon, we're going to show that there exists a partition. I'm calling it P of epsilon, so dependent on that epsilon, such that the upper sum with this partition minus the lower sum with this partition is less than epsilon. So that's what we're trying to show. All right, so we got to choose epsilon greater than 0. All right, and I guess I should have stated this before I'd done the proof. So this is going to be in yellow. Everything that's in blue is part of the proof. Yellow is sort of the thought process. But one of the thought process that I'm going to use is the analytic definition of sup and imp. And for supremum, U equals the supremum of some set A if and only if for all epsilon, there exists an element A and A, so that when we do U minus epsilon, that's less than this some element A. Now for the infimum, let's say W equals inf of some set B, if and only if for all epsilon, there exists a B and B. Sorry about that, my cats are fighting, but got it settled now. So W equals the inf of B, the infimum of some set B, if and only if for all epsilon, there exists some element B in capital B, so that essentially W plus epsilon is not a lower bound. So that means that W plus epsilon is greater than this element B. All right, so that's just using the analytic definition of sup and inf, and we're going to use that to our advantage. Okay, so now back to the proof. So we choose an epsilon greater than 0. So since L of f is the supremum of all lower sums, and I'm using partition P, then there exists a partition P so that its lower sum, so we want to fit this definition so that the lower sum with P is going to be greater than L of f. And since this is true for all epsilon, I'm going to do L of f minus epsilon over 2. And you'll see why I do that in the proof. Okay, so that's that case. And the same thing, similarly, since U of f is the inf of the upper sums, and I was using all partitions Q, then there exists a partition Q so that, now in this case we want to fit this definition so that the an upper sum with this partition Q is less than U of f. And again, it's all true for all epsilon, so it's going to be less than U of f plus epsilon over 2. All right, so we have those two things. Now we want to combine this information together, so we're going to make a refinement. All right, so let P of epsilon be the common refinement of this particular P and Q. So what do we know about refinements? So we know the lower sum, lower sums are going to get greater. So like the lower sum of P is less than or equal to the lower sum of P of epsilon, and that's less than or equal to the upper sum of P of epsilon, and that's less than or equal to the upper sum with Q because of the refinement. All right, so then focusing on just this part and combining it what we stated earlier. So lower sum of this particular refinement P of epsilon is greater than or equal to this pretty much all partitions P. And for that specific partition P, we have that is greater than L of F minus epsilon over 2. This is greater than L of F minus epsilon over 2. Well, that's true if and only if we negate everything, multiply by negative, we have negative L of P of epsilon is less than or equal to negative L of F of P, which is less than negative times L of F minus epsilon over 2. Okay, so therefore, and let's see, so we have that, and we also know that upper sum of P of epsilon is less than or equal to the upper sum with Q for all Q, and in particular, the specific partition Q in which we're using the upper sum with Q to be less than U of F plus epsilon over 2. So therefore, if we combine, hence when we do the upper sum of our partition P of epsilon, combining with minus the lower sum of partition with epsilon, well, we know the upper sum of that is less than or equal to the upper sum with Q. And we know that the negative of partition P of epsilon is less than the negative of partition P. So this will be less than U of F of Q minus L of F of P. And we know U of F of Q is less than, so that's less than U of F plus epsilon over 2. And then negative L of F of P is less than the negative of L of F minus epsilon over 2. So this would be less than and then minus L of F minus epsilon over 2. And what does this give us? So we distribute the minus, we get U of F plus epsilon over 2 minus L of F, and then negative times negative makes that plus epsilon over 2. But we know that these are equal since we're assuming F is Darboux integrable. And so those cancel each other out. And so you just have epsilon over 2 plus epsilon over 2, which is epsilon. So this, all of this, that's equal to epsilon. Therefore, we formed a refinement P of epsilon so that U, the upper sum of it, minus the lower sum is less than epsilon for all epsilon, since epsilon was arbitrary. All right, so that completes the proof in that direction. Now the other direction. So this time we're going to assume for given epsilon, there's a partition P of epsilon so that the upper sum minus the lower sum is less than epsilon. All right, and we're trying to show that f is Darboux integrable. Okay, so we're trying to show f is Darboux integrable in other words, L of f equals U of f. That's what we're trying to show. All right, so we know U of f is the infimum of the upper sums. L of f is the supremum of the lower sums. So we can say that, let's see, so L of f is supremum. So we know our particular lower sum with partition P of epsilon is less than or equal to L of f, because that's our sup of the lower sums of all partitions. And so that's true if and only if negative of L of f of partition P of epsilon is greater than or equal to negative L of f. Okay, so that's, we know that, and we know for the upper sums, U of f is less than, since that's our infimum of the upper sums. So the inf of all upper sums, partition Q, that's for all Q, and that's equal to U of f. That's, since it's the infimum, it's less than or equal to our upper sum of partition P of epsilon. So therefore, when we do U of f minus L of f, that's less than or equal to, so our U of f is less than or equal to the upper sum with partition epsilon, P of epsilon. And we know negative L of f, that's less than or equal to negative lower sum of partition P of epsilon. So this will be U upper sum of partition epsilon minus the lower sum of partition epsilon. And we already know that this entire thing, L of our upper sum minus the lower sum, we're assuming that's already less than epsilon. So this would be less than epsilon for all epsilon greater than 0. And so we have the upper sum minus lower sum is less than epsilon for all epsilon. This is equivalent to saying the upper, or U of f minus L of f is less than epsilon. So that's equivalent to saying U of f minus U of f equals L of f. And that's what it means to be Darboux integrable. All right, so hopefully that made sense. I think that direction was much straightforward. The other direction was a little bit more complicated. I'll just quickly read through it. So the harder direction, we assumed f was Darboux integrable, which means L of f equals U of f. L of f is the sup of all the lower sums of all partitions P. U of f is the inf of upper sums of all partitions Q. And so I basically wrote down that for all partitions Q and all partitions P, we have lower sums are less than or equal to the upper sums, and lower sums with all partitions P is less than or equal to L of f, which is equal to U of f, and that's less than or equal to U upper sums of all partitions Q. We wanted to show that given epsilon, there exists a partition P of epsilon so that the upper sum minus lower sum is less than epsilon. So choose epsilon greater than 0. And then I use the analytic definition of sup and inf. And in particular, I said since our L of f is the supremum of the lower sums of all partitions P, then there exists a partition P so that the lower sum of that partition P is greater than L of f minus epsilon over 2. So that met this requirement. And so since U of f is the infimum of all upper sums of Q, then there is some partition Q so that its upper sum is less than U of f plus epsilon over 2. And that's where I use this requirement. So then let P of epsilon be the common refinement of these particular partitions P and Q. So then we know that the lower sum of P is less than or equal to the lower sum of P of epsilon, which is less than or equal to the upper sum of P of epsilon, which is less than or equal to the upper sum of Q, since that's a refinement. So we have that the lower sum of partition epsilon is greater than or equal to the lower sum of partition P, and that partition P is such that its lower sum is greater than L of f minus epsilon over 2. So then that's if and only if I multiplied everything by a negative that reversed the inequality signs. And then we know that the upper sum of P of epsilon is going to be less than or equal to the upper sum of Q. And for this particular Q, it's less than the U of f plus epsilon over 2. So I just combined that information and did the upper sum of partition epsilon minus the upper sum of partition, or minus the lower sum of partition epsilon. U of f of partition epsilon is less than or equal to U of f of Q. And then negative L of f of partition epsilon is less than or equal to negative L of f of P. U of f of Q is less than U of f plus epsilon over 2. Negative of L of f of P is less than negative times L of f minus epsilon over 2. And that pretty much gave us epsilon when you distribute the minus sign and use the fact that U of f equals L of f, so those cancel each other out. So that was how I did that direction. All right, so that's where I'll complete this video.